Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design. Module 5 Synchronous Counters and State Machines. In the last class, we have designed a synchronous 3-bit up counter and understood the working of the circuit. Today, we are going to design a 3-bit down counter using JK flip-flop itself. So a down counter basically counts in the reverse direction. Here also, since the number of input bits is 3, the maximum number of states the counter can count is again 8 itself. The only difference is that the sequence should be like this, starting from 0, 7, 6, etc. up to 1 and resetting to its initial state 0, and the sequence will be continuing. Here, since it's a down counter, the counting sequence will be decreasing in nature. That is, for each clock pulse, the counter will reduce its value by 1. Here you can see in the state diagram, initial state is 0, 0, 0. On obtaining the first clock pulse, the counter changes its state to the next value, that is 1, 1, 1. And similarly, for each clock pulse, the counter reduces its value by 1, and on the 8th clock pulse, the counter resets its state to again the initial state 0, 0, 0. Based on the state diagram, we have to complete the design table. So initially, we are writing the present state one by one. Each state is written in a row. First state is 0, 0, 0. Next state is 1, 1, 1. And finally the last state as 0, 0, 1. Now we have to complete the next state column. Since first state is 0, 0, 0, next state will be 1, 1, 1. Similarly, if present state is 1, 1, 1, the next state will be 1, 1, 0, and like that. And for last state 0, 0, 1, the next state will be 0, 0, 0. Now we have to complete the remaining columns by considering the excitation table. Once the design table is completed, now we have to use the design table entries for populating the K-maps. On the left bottom, we can see the K-map for input JA, and on simplification, JA is equal to QB bar QC bar. Similarly, on the right bottom side, we can see the K-map for KA, and on simplification, KA is equal to QB bar QC bar. On the left top side, we can see the K-map for JB. On simplification, JB is equal to QC bar. On the right top side, we can see the K-map for KB, and on simplification, KB is obtained as again QC bar. Left bottom, we can see the K-map for JC, and on simplification, JC is obtained as 1. And on the left right side, we can see the K-map for KC. Here also on simplification, KC is obtained as 1. Now using the minimal expression for each of the flip-flop input, the logic circuit diagram is completed and is as shown in the figure. Now to understand the working of the 3-bit down counter, let's have the simulation of the circuit. So before starting the counting operation, let's check the asynchronous input. Upon making the preset input to 0, all the flip-flop will be set to 1, and upon making the clear to 0, all the flip-flop will be reset to 0. In this circuit also, the first flip-flop is the LSB and the last flip-flop is the MSB. Initial state is 0, 0, 0. All the flip-flop are in the reset state. On the first clock pulse, the flip-flop out changes to 1, 1, 1. Next clock pulse, output is 1, 1, 0. Next clock pulse, output is 1, 0, 1. Next clock pulse, output is 1, 0, 0. Again giving the next clock pulse, output is 0, 1, 1. For the next clock pulse, output is 0, 1, 0. Next clock pulse, output is 0, 0, 1. For the next clock pulse, output is again 0, 0, 0. Thus we have completed one cycle of operation, starting from 0, 0, 0 and again coming back to the starting state 0, 0, 0 itself. So as far as a down counter is considered, for each clock pulse, the counting state will be, or the equivalent binary value will be reduced by 1 The bottom portion of the slide represents the timing diagram of a down counter. Here also, for each of the clock pulse, we can observe the variation in all the flip-flop outputs. For first clock pulse, initially the flip-flop outputs are 000. At the end of first clock pulse, output changes to 111. At the end of next clock pulse, out changes to 110 and so on. And at the end of the 8th clock pulse, the output reset back to its initial state 000. So with this, I hope you have understood the design and the working of a 3-bit down counter.